So let us start from this topic, electronic configurations and types of elements, S, P, T and F block. So for now we have seen like group-wise electronic configuration and period-wise electronic configuration. So we have seen what is the basis of the periodic table. So now we will be talking about electronic configuration and types of elements, S, P, T and F block. So these blocks are divided and there are four blocks, S, P, D and F. So the above principle, that is the build-up principle, and the electronic configuration of atoms provide a theoretical foundation for the periodic classification. The elements in vertical columns of the periodic table constitutes a group or family and exhibit similar chemical behavior. So in a vertical column, all the elements of that particular group exhibit similar behavior. That is because, as we have already discussed, that it has same number of valence electrons, right? So definitely it will have something in similar. So they have similar chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in their outermost orbital. This is very important point. So we can classify the elements into four blocks like S block, P block, D block, and F block. So when your electron is filled in the S block, so that particular element is put in S block. Similarly for P block, D block, and F block. So depending on the type of atomic orbitals that are being filled with electrons. So why some elements are placed in S block and why some elements are placed in P block? So you can say that it depends upon which orbital is filled by the electrons. So if S orbital is filled by electrons, so that particular element will be kept in S block. And if P block is filled by electrons, then that particular element will be placed in the P block section. So this is illustrated in figure 3.3. So what is figure 3.3? So this is figure 3.3. Okay. So in S block, so all the elements here, 1s is being filled, here 2s is being filled, 3s is being filled. For here D block, here for like scandium to zinc, 3D is being filled. Okay. For this period, like fifth period, 4D is being filled. For P block, 2B is being filled. So, and for N block, all the F orbitals are being filled. So you can get this information. So it is illustrated in figure 3.3. We notice two exceptions to this categorization. Strictly helium belongs to S block, but it is positioned in the P block, right? Along with the other group 18 elements is justified because it has completely filled valence shell 1s2 and as a result exhibits properties characteristics of other noble gases. So here you can question why helium, in case of helium 1s is being filled, it is 1s2, then why it is not here? It should be here anyways, there is gap here, right? So why it is not here and it is placed in the 18th group? So the explanation for this is that though 1s is being filled, but it has 1s2 configuration, that is it has filled orbital configuration, which makes it in the category of group 18 elements, that it behaves nobly. Okay, it is, so that is why it is kept in the group 18 elements. Okay, so it has filled valence shell electron, and all the filled valence shell electron elements are there in the group 18 elements. So the other exception is hydrogen. It is only one. It has only 1s electrons and hence can be placed in group 1, that is with the alkali metals. It can also gain an electron to achieve a noble gas arrangement and hence it can have similar. It can behave similar to group 70. That is the halogen elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure 3.2 and figure 3.3. We will briefly discuss the silent features of the four types of element marked in the periodic table. More about these elements will be discussed later. During the description of their features, certain terminology has been used which has been classified in section 3.7. So all of these are not of importance. The important thing is that helium is placed in the 18th group, that is in the P block, though here no P block no p orbital is being filled. Here one s is being filled, but since it has the filled valence shell electronic configuration, so it is kept with the elements that has also the filled valence shell electronic configuration. Hydrogen is kept separately. So hydrogen, in hydrogen, one s is being filled, so it should be kept with other alkali metals here, right? But it is not here, and it can also be kept in the group 70. Why? Because if you like, it is written over here, it can also gain one electron, so it is 1s1. So if you give one electron to hydrogen, then where it should be placed? Then it will become like noble gas, right? So for group 17 elements also, if you give one electron to fluorine, it will become neon. So it should be placed. It can be placed in the group 17 as well. It will behave like group 17 elements. But so in order to get rid of this, like where to keep hydrogen, so it is kept separately in the periodic table. So let us talk deeply about the S block elements. So the elements of group 1, which is called as alkali metals, and group 2, which is termed as the alkaline earth metals, which have NS1 and NS2 outermost electronic configuration, belong to the S block elements. We know this. So they are all reactive metals with low ionization enthalpies. They lose the outermost electrons readily to form +1 ions in case of alkali metals and +2 ions in case of alkaline earth metals. So the metallic character and the reactivity increases as we go down the group. Because of high reactivity, they are never found pure in nature. So the compounds in the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. So it is talking about the S block elements where you have alkali metals and alkaline earth metals. So it is 1s1. It is adds to be S1 and S1, I would say, general terms, and NS2 for the group 2 elements. So it for group 1 element, it can easily lose one electron and form 1s0, which is again stable. So this can easily form like ionized to +1 state, and this can easily ionized to +2 state. So, and the ionization energy, that is the knocking out of electron from the shell, is the energy required is very low for all of these cases. So these elements, these metals are very reactive and generally exist in the ionic, only with the exception of lithium and beryllium. As you go down the group, this ionization energy further decreases because the electron is when you're going down, then the size is increasing. We will be discussing all of this. For now, you get to know this. Like when you're going down the group, then the size increases, okay? So when you go down the group, the size of the element, or we can say atom, increases. So that means nucleus and the outermost electron that needs to be knocked out, the gap between them also increases. Okay, so that means they are actually attracted with the electronic forces, right? Because like this is this nucleus is positively charged, electron is negatively charged, so it has attractive forces. But when you go down the group, size increases, so the distance between the outermost electron that is to be ionized and the nucleus, it is actually denoted by capital N. So in the nucleus, the distance increases, and hence it is more easier for the lower elements, the down elements, to knock out its electron, and hence ionization energy decreases. Ionization energy decreases means you need less energy for now to knock out the outermost electron. Okay. So let us talk about the p block elements. So what p block contains? So the p block elements comprise of those belonging to group 13 to group 18. You better know this. And these together with S block elements are called the representative elements or main group elements. So this block, this S block and this P block, when you combine them and say it together, they are called the main group elements. This is the D block, it is not in the main block, the main group elements. Okay, so The outermost electronic configuration varies from ns to np1 to ns to np6. We already know this because p orbitals are being filled, and that is why these elements are placed in the p block. So at the end of each period is a noble gas element with a closed valence shell, and that is why helium, which has a configuration of ns2, again a filled valence shell, is placed in the group 18. So all of the in the group 18, all of the noble gas elements are there, which has the closed shell, valence shell configuration. Why they are noble? Because they do not react with much. Okay. All these orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter the stable arrangement by the addition or the removal of electrons. So the filled orbital state is very stable. So it is very difficult to either ionize an electron or add an electron. It is impossible to add an electron in the valence shell because it is already filled, but it is not possible also to alter any electron. Like you cannot knock out an electron. It's very difficult to knock out an electron from the noble gases. It is not impossible, but I am telling it is very difficult. It is very high in energy, and that is why these are called noble, because they do not react with other elements. Okay, so the noble gases thus exhibits very low chemical reactivity. That is what I was talking about. Preceding the noble gas, this preceding means just before the noble gas, that is the group 17, chemically important group of non-metals. Okay, so here we saw in the S block all are metals, right? But for here, there are certain elements that are non-metals. These pink ones are the noble gases. These green ones are the non-metals. This blue ones is defined by the metals, and here also all the metals are there. And this red ones, they have both the properties of metals and metalloids, some properties of metals, some properties of non-metals, and that is why they are called metalloids. Okay, so we are talking about the group 17, which is just preceding the group 18 elements. Also, it is very important, and most of them are non-metals. Okay, they are called halogens, and group 16 are called chalcogens. Okay, group 16. These two groups of elements have highly negative electron gain enthalpies and readily add one or two electrons respectively to attain the stable noble gas configuration. So the non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. So when will a metallic character of the particular element will increase, and when non-metallic character will increase? It is very, very simple. So for metallic character to increase, it has to be in the positive state, like it has to knock out its electron, right? So a good metal, more reactive metal are those metals that can easily get rid of the electron. Okay, so as we know already, we have discussed that as we go down the group in the period in the group, the ionization energy decreases. Hence, when we go down the group, then the metallic character also increases. You can see when you are going down, this last metal is metallic. When you go down, this last metal, last element is metallic. Here there is something in between. Okay, and also when you go from left to right, like non-metallic character is just opposite to that of metallic character. So for metallic character, you need to knock out the electron from the valence shell. But for non-metallic character, you need to gain electron. So with those elements that can easily gain electron will be more non-metallic in nature. So you can see from here, when you go from left to right, so fluorine and oxygen, considering comparing both, so fluorine has to gain one electron to get to its noble gas configuration, which is very, very stable, and oxygen needs two electrons. So it will gain one electron and then form negative charge in oxygen. And again, gaining another electron to come to its noble gas, it's difficult, right? But it does, because you already have one negative charge on oxygen, and then again you have to gain one electron to that negative charge. So this electronic repulsion will be there. So it is kind of difficult. So it is said that from when you go from left to right, the electron gain enthalpy becomes more negative. So electron gain enthalpy becomes negative means, since gaining of electrons is exothermic in nature, okay? Because when you get some electrons, so like you get some free electrons, so free electron has energy of 0. So when you trap that electron to the element, then it has a energy of negative, some energy is released. So it becomes less negative when you go from left to right. And you now know why. The non-metallic, okay, fine. This is very important. Now let us talk about the D block elements. That is the transition elements. What is transition elements? We will be talking about that. So these are the elements of group 3 to 12 in the center of the periodic table. They are not considered in the main group elements. These are characterized by the filling of the inner d orbitals by electrons and are therefore referred to as D block elements. True? These elements have the general outer electronic configuration of n-1d 1 to 10 and s 0 to 2. Why 0 to 2? That also we will be discussing. So let us discuss it now. Okay. Let us go to the periodic table and then we will discuss. So yes, you can see over here that let's talk about 3D copper and also see nickel and also see zinc. So for nickel, the electronic configuration is 3d8 4s2. So according to everyone, what should be the electronic configuration for copper? It should be 3d9 4s2, but it is not 3d9 4s2. It is rather 3d10 4s1. So this is because of the energies of these orbitals. Like when 3d9 is there and when 4s2 is already there, then what happens is that one electron from 4s2 comes to 3d9 and make it 3d10, and thus this is energetically favorable. Okay, and now here the electron is added in the s block. Okay, so this happens. So that is why the general configuration of these 3D elements is n-1 d 1 to 10 and ns 0 to 1. Okay. For palladium, you can see it is 4d10. Okay, it is 4d10 and it is not 5s and it is 5s0. So all these two electrons are shifted. So this is more stable. So it is all this electronic configuration, the changes in the electronic configuration is because of the stability. And obviously these all are the metals. These transition elements all are metals here. They mostly form colored ions, exhibit variable valence, that is the oxidation state, because you have 3D, right? So it can show a variable oxidation state, paramagnetism, and oftenly used as catalysts. However, zinc, cadmium, and Hg, which have the electronic configuration of n-1d10 and ns2, does not show most of the properties of the transition elements, because here actually D block is not filled. Okay, here S is filled. We all know this, right? But it is placed in the D because it should be placed in the D, and in a way, so that is why it does not behave like other transition metals. In a way, transition metals from a bridge between the chemically active metals of S block elements and the less active elements of group 13 to 14, and thus take their family's name transition elements. So now you know why it is called transition, because from metals to non-metals, or we can say from reactive elements to non-reactive elements, there's a transition, and these kind of, this is like a transition. Okay, so you're going from here to here by this. So this is like transition. That is why transition. Now let us talk about the last block element, that is the F block elements, that is not present in the proper periodic table, but it is separated. So the two rows of the elements at the bottom of the periodic table, that is called the lanthanoids. Z is equals to 58 to Z equals to 71, and actinoids Z equals to 90 to Z equals to 103 are characterized by the outer electronic configuration of n-2 F1 to 14, n-1 D01, again similar trends, and S2. So the last electron added to each element is filled in the D block, F block. Okay, So these two series of elements are hence called the inner transition elements. That is actually, it needs to be placed here, like after this you have all the lanthanoids, after this you have all the actinoids. So that is why it is inside the transition elements, but it is not there in the transition elements. That is why it is called inner transition elements. Okay, all the S block elements, they are all metal again, and within each series the properties of the elements are quite similar. That is why they are kept separately. It was the properties were not matching with the 3D element, sorry, with the transition elements, and that is why they are kept separately, and their basically properties are similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoids elements. Actinoid elements are radioactive. Okay, so many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The element after uranium are transuranium elements. So all of these are transuranium elements. They are also called transuranium elements. Actinoids are not studied much because though they are kind of metals, but they are metals, they are all metals actually. But after uranium, from uranium, or we can say most of the actinoids are radioactive, and that is why their characteristic features are not studied much. So let us talk about the problem 3.3. So the elements Z equals to 117 and 120 have not yet been discovered. In which family or group would you place these elements, and also give the electronic configuration in each case? So Z117. So see the periodic table and see where it needs to be. So this has not been made, right? So 117. So 117 will show similar properties to that of group 17 elements. It needs to be placed here. And the another question was what? 120. So 120 is not here. So it will be where? 118, then 119 and 120. So it will be here somewhere below RA, and it will have similar properties as that of group number 2. Okay, so it will have 8s2, and it will have 7s2 75. Okay, so 8s2 and 7s2 75, right? So metals, non-metals, and metalloids. So we already learned that which elements are metals, which elements are non-metals, and what are metalloids. So let us talk about it. So in addition to displaying the classification of elements into S, P, D, and F blocks, shows other broad classification of elements based on their properties. So this classification to S block, P block, D block, and F block is based, given on the basis of the last electrode that is being filled in the orbital. So it is another broad classification of the elements based on their properties. So the elements can be divided into metals, non-metals, right? So metals comprises more than 78% of all the known elements. So in the periodic table also, it's 78%, more than that are metals, okay? And they generally appear on the left side of the periodic table. All the S block elements and all the 3D and all the transition elements, all the F block elements are metals. So metals are usually solid at room temperature. You all know that has very high boiling points. Mercury is an exception, and gallium and cesium also have very low melting points. So we are talking about melting points. When we are talking about solids, then we are not talking about boiling point, because boiling points liquid will be talked about. So have very so generally solids, metals are solids, and generally they have very high melting point. There is an exception here. Mercury is liquid at room temperature, and gallium and cesium also have very low melting point, 303 Kelvin and 302 Kelvin respectively. So metals usually have high melting and boiling points. Okay, they are good conductors of heat and electricity. Why? Because they can easily knock out its electron. Okay, and an electron can easily participate in conduction of heat and electricity. So they are malleable, that it can be flattened into thin sheets by hammering, and ductile, it can be drawn into wires. So they are malleable, they are ductile. So in contrast, non-metals are located at the top right side. Why top? Because down again, metallic character increases when you go down the group. So down are also metals, and some of them are non-metals, not metalloids. So right side and the top. So the top right hand side of the periodic table are non-metals. Very few of them. Very few of the known elements are non-metals. So in fact, in a horizontal row, the properties of the elements change from metallic on the left to non-metallic on the right. We know this is because of the more negative electron gain enthalpy when we move from left to right. So the non-metals are usually solids or gases at room temperature with low melting and boiling points. Boron and carbons are exception. They have very high melting boiling point. They are poor conductors of heat and electricity because they cannot knock off its electron. So who will conduct the heat and electricity, right? So they are non-conductors of heat and electricity. Also, they're not malleable, not ductile because they're very, very brittle. And so the elements become more metallic as we go down the group. Already know we, right? The non-metallic character increases as we go from left to right across the periodic table. This we have already discussed. The change from metallic to non-metallic character is not abrupt as shown by the thick zigzag line. Okay, so it is not that you'll have metallic and then again you have non-metallic. There is something in between. You have metalloids, those elements that has some of the characteristic of metals and some of the characteristics of non-metals. So the elements, example, silicon, germanium, arsenic, antimony, and tellurium. Bordering this line and running diagonally across the periodic table shows properties that are characteristic of both metals and non-metals, and such elements are called semi-metals or metalloids. Okay. Now there's a problem 3.4 which we will be dealing in this particular lecture. So considering the atomic number and position in the periodic table, arrange the following elements in the increasing order of the metallic character. Okay. So you need to arrange it according to the metallic character. So we know that when we go from left to right in a periodic table, then the non-metallic character increases, and when we go from top to bottom in a group, then its metallic character increases. Okay. So let's go to the periodic table to answer this question. This will help. Okay. So and you need to arrange it, okay, in the increasing order of metallic characters. So this means that you will keep those that element first which have the least metallic character. Silicon, barium. Where is barium? Here, right? Just okay. Top and before. Magnesium, sodium, and phosphorus. So you already know this. Phosphorus is the rightmost side, so it has to be least metallic. Okay, so keeping phosphorus first has the lowest metallic characteristic, and then we have silicon. Then we have here what is left is beryllium, magnesium, and sodium. So the topmost is the least metallic. So, and also when you go from left to right, so there's metallic. So beryllium and sodium again have almost similar trend, right? Because when you go from left to right, the non-metallic character increases. Again, you go from a non-metallic character is increasing, and you're going down. So metallic character is increasing. So this means that now this is very clear. So beryllium will have less metallic character in comparison to these three, and after that, magnesium and then sodium. So this is the answer. I hope it is clear for you. Let us see what is the answer. It is phosphorus, silicon, beryllium, magnesium, and sodium. So it is same, and I think it is clear to everyone. And this after this, periodic trends properties of elements will be discussed later in the next subsequent lectures.